Hello everyone. I hope you have had a good weekend and then now you are ready for our week number 7 if I'm not wrong. Thank you for being here. Thank you for all of you that submitted the written work for test number 1. I will be working with test number 1 this week. Maybe tomorrow I will post your grade. Today we are going to start the material for test number 2. Like I mentioned on the last announcement, in my opinion, test number 2 is the most difficult test on the course, and is because the level of all the concept that we are going to be studying on test number 2, it could be a little bit abstract, and it has a lot of material. It contains a lot of material that we need to understand before getting into the technical part of test number 2. Okay? The good thing is that once you get and you understand the method and the properties that we are going to be using, it becomes very mechanical. It becomes very straightforward. And when you solve the exercises, but the problem first is to get a complete understanding of what's happening in order to get the correct answers. All right. So I'm going to jump and start with our class because I'm going to take a little more. I'm going to take more time that I'm used to take for the classes because I want to go over the material for unit number 5. I want to give you an introduction. It's going to be a review of what you have seen from the episode videos, okay? And maybe we can go a little more deeper on what's happening in this unit, right? All right, so I would like to start with, if I can move this to the right position, with an introduction to polynomials. All right. So to go and do our introduction for polynomial functions, first let's just check out how we got to this theme of polynomials. From the beginning of the semester, we start working with relations. All right, an example of a relation is a relation between variable x and y, and there you have it, right? We have an equation that relates x and y. From the relation, we went to the functions, and we know that functions are a special kind of relation. The same equation that we have here is the same equation that we are going to have here for functions. The only thing that we change is the notation. Now, instead of using y, we are using f of x, right? But we are talking about a relation, a special kind of relation, which is a function. Now, we are going to talk about a special kind of functions, and those are the polynomial functions. Polynomials. All right. And again, we are not changing anything here yet on our example. The only thing that I'm changing is just the name, basically, of the relation. For function, you use f of x just to give that equation a name, a function name. For polynomial, now, because we are talking about polynomial, I just changed its name to p. But we are talking about the same. We are still working with relations. a special kind of relations. So focusing on polynomials, a general definition for polynomial, and this definition is going to be very mathematical in that sense. So don't get discouraged when I'm going to write here. I'm going to show you then examples on, and then you will get a more easy definition to understand. But I want to start with the definition that a lot of books provide to us. So usually when the books define a polynomial, this is how they present the polynomial. A sub n times x to the power of n, and then from that point we go one index less, so a sub n minus 1, and then the power will be n minus 1, and so on, right? So the next one will be a sub n minus 2, and then x to the power of n minus 2, until we reach the constant term. See that here a is 1, so the power of x is 1, so we do not write that. And then we have the constant term, so a sub 0, x to the power of 0 is just 1, so here is the constant term. All right. So this also is the standard form for any polynomial. You are seeing that I'm using the plus or the addition operation to separate the terms. These three dots here means, because this is a general definition, we do not have a value for n, it just is a representation, but we know that n is going to be a number, and from that number we go one value less for every term. So in these three dots, there's a representation of all those terms. But again, I don't want you to feel discouraged by this definition. This is a very abstract definition. Just in a moment, I'm going to present to you examples where this definition is going to make more sense. Okay, I just want to lay out all the theoretical parts here, and then we jump to the examples. From here, what I want to do from here is the following: is to give names to this concept, to these elements of the definition. All right, so what you have in pink is what we are going to know as the coefficients. All right, so a sub, in this case, I'm going to use the letter I to represent all of these subindex or subscripts. A are the coefficients. Okay, and you can recall this from the past unit where we worked with quadratic functions, where the coefficients are the first thing that we see on any term when we write that function, the quadratic function, in a standard form, right? Important the general definition of polynomial. Okay, we have some specifications. Those coefficients are real numbers, all right? So each representation of the coefficient is a representation of a real number, right? And we know, or a sub n, the first coefficient that we are seeing here in the standard form, it is the leading coefficient. Okay. So because a sub n is the leading coefficient, now we know that this term here is the leading term. All right, and you are going to know which of all those terms is the leading term based on the exponent. The greatest exponent, or the term with the greatest exponent, is the leading term. Talking about the exponents, those are also important because we use them to, like I said, to identify the leading term, but also they define the degree of the polynomial. And they also have important properties that they need to meet in order to have a polynomial. So n is the power of each variable here. So we know that that is the exponent. Okay. The property on the exponent are it is critical because the polynomial will define of a polynomial will be determined, if we have a polynomial or not, will be determined by the exponent, the type of exponent we have, right? So for the coefficients, there's no more restriction. The coefficients are real numbers, but for the exponent, we need to have positive or zero. The value for the exponent are going to be positive or zero, and you can see that we have an exponent of 0 here because on the constant term, x raised to the power of 0 is just 1, so it gets cancelled. So we can have n equal to 0. We can have an exponent equal to 0 because when n is equal to 0, we have the constant term. Okay? So maybe I should put this here. N equals 0 means the constant term. Okay? The rest of the exponents need to be positive. Okay? And they need to be integers. Okay? Integers or whole numbers. And like I mentioned, the greatest or the maximum value, or the greatest n value, is the degree of the polynomial. All right. So this is a very mathematical take on the general definition of what a polynomial is. Now let's compare this mathematical definition with examples so we can have a better understanding of this definition. So let me move this to the next page. Right, phase 2. So I'm going to shrink this because we are just going to use this picture as a reference. Maybe I should put this here. All right. So let's see examples of polynomials. Okay. So here our first example. So you can see here that first, the coefficients here are, let's identify the coefficients. Okay, I think you can see what they're here. Coefficients. Coefficients are 3 and 2. All right. We have the leading coefficient is 3. The constant term is 2. All right. And the degree of this polynomial is 1, right? When we don't write the exponent, it means that its value is 1. So the degree is 1. This is also a linear function. All right. So see that I'm writing our linear function in the standard form because I'm following the order of the term. The leading term is 3x to the power of 1. So that's the leading term. From there, we can take the leading coefficient, which is 3. And next to it, we have the constant term. All right. Where the constant term has an exponent of 0 in its variable x. Hence, we don't write the variable x there because it gets cancelled by that. Right? So we are seeing here something that we have studied before. This is a linear function, but the linear function is also a polynomial of the degree of 1. Okay? You can also relate the leading coefficient here with the slope of this linear function. Right? So each element from this function, it contains its properties and it is important. The other equation, or the next example that we are going to see, is an example that we have, or a type of polynomial that we have worked with it before, and this is a quadratic equation. We are seeing that we have this quadratic equation. It is not 100% in standard form because this here we are seeing a minus instead of plus and -8, right? But we can say that we have some kind of the standard form. At least we have the structure where the leading term is the first term that we are seeing from left to right. Then the next term that we are seeing, and the power of the variable is 1 degree or 1 value less than the power of the term on the left. Okay, and then the last term that we are seeing is the constant term. So from here, we know that the coefficients are -2, +4, -8. Leading coefficient being -2, the constant term being -8, right? The other thing that we can identify here is the degree. The degree is 2, and we know that because of the greatest power that we are seeing here, which is 2. So this is a quadratic function. All right, my face is in the middle, but there is a name, quadratic function. Okay, this is something that we have studied before, Unit 4 to be precise. Okay, and you can recall from Unit 4 that we talk about and we study the properties of a quadratic function to solve real-life problems. Okay, and we are going to do the same on test number 2. We are going to be working with different polynomials, different degrees polynomials, but we are going to do exactly the same as we did on unit number 4, where we go over all the properties that are related to that particular polynomial, and based on those properties we are going to solve real-life problem. In this test, though, we are not going to go deeply, we are not going to talk about too much on real-life problem. We are going to focus more on those properties. Okay? But on future classes, maybe engineering classes or computer science classes, I'm talking about the material that I know, you are going to see where the property that we are going to learn here are going to where you are going to use those properties, where you are going to apply those properties. Okay, test number 2, we are going to be more focused on the properties itself. Later on during your college or academic career, you are going to know where you are going to use those properties and how to apply them, right? Another example that I want to give you is a cube function. Right? Okay, so from this polynomial, first we can see that we have the structure of the standard form, where we can see the first term being the leading term, and then we can see that the next terms goes in order, in decreasing order in terms of the exponent, so 3, 2, 1, 0. From here we have the coefficients. Coefficients are 8, 7, -8, -7. Leading coefficient is 8. Constant term is -7. And degree is 3. So this is a cube function. All right. Let me give you one more, and this time I'm going to give you a not ordered polynomial. So that's the equation. Let me see if you can see it. Yeah, you can see it. All right, and I will want your help here. I want you to tell me, the first thing I want you to tell me is this polynomial? Is this the standard form of this polynomial? What do you think? It is no. This is not the standard form. All right. So we are seeing from these three terms that the greatest exponent is 5. So we know that the degree is going to be 5. All right? So let me rearrange this. And I believe, Tristan, you put it here. If I can bring down the chat. I need to see this. All right. All right. So Tristan wrote this on the chat. And this is completely correct. So we can say that this is the standard form in a simplified version of the standard form. Because if we have a power of 5, maybe we are missing some terms. Before going to that, let's identify the coefficients. What are the coefficients here? How many coefficients do we have here? Okay, -3 that's the leading term, yeah, the leading coefficient. We have 7, we have 2. All right, but what if I tell you that you are not 100% right, because you are missing some coefficients, and those coefficients are the following. So you are seeing that there's a gap between 5 and 1, right? Those are the exponent that we are seeing here. But between them, between these two terms, the leading term and 7x to the power of 1, we have the term with x to the power of 4, with x to the power of 3, with x to the power of 2. And this is the complete standard form of that polynomial. All right? It is not necessary to write all the terms when coefficient is 0, but this is something that you need to know. Whenever you see this, you need to know that there are 3 terms with coefficient equal to 0. Hence, we are not seeing them there, because 0 times something, it is 0. So those terms are to get cancelled. But to write the complete list of the coefficients, we have -3, 0, 0, 0, 7, and 2. Leading coefficient is -3. Constant term, it is 2, and the degree is 5. All right. We don't have like a special name for the function here, just a function with degree 5, right? Okay, so from here you have seen 4 examples of what a polynomial is and how to identify the coefficients, the leading term, the constant term, and the degree. Okay, also you saw how to rewrite or to write the standard form of the polynomial. Okay, keeping always in mind that we need, if we want to write the complete standard form of a polynomial, we need to take into consideration terms that its coefficient might be 0. Okay, those coefficients cancel the entire term, but they are there. All right. So I'm going to copy this one because this polynomial is going to be our subject through the rest of our class. All right. Okay, so we have page 3 here. So what we know so far from our class. We know that functions can be represented as graph in the coordinate plane, right? From those functions, we know how to identify the x and y intercepts. All right. So when we identify the x-intercept, we know that the y value is equal to 0. And when we identify, or when we have any y-intercept, the x value of that point is going to be 0, or the x of that coordinate is going to be 0, right? So we know functions. We can represent those functions as graph, unique graph in the coordinate plane. We can identify the intercepts of those graphs. So the x-intercept is whenever a point has a y-coordinate of 0. The y-intercept is whenever a point has a x-coordinate equal to 0, right? Or we can say that whenever the graph touches the x-axis, that's an x-intercept, and for the y-intercept, whenever the graph touches the y-axis. We also know how to identify the local or relative max and minimum value. We know how to identify its location and its value. Remember the contrast, or how we use the coordinate. X is to represent the location, y is to represent the actual value. We also know how to identify domain and range. Domain being the set of all the x values, and range being the set of all y values. So that's what we know so far from functions. Now, how we are going to see this in polynomials? And that is what test number 2 is about. We are going to take a step further, or a deep step on the properties from the graph, the intercepts, the local, the relative max and minimum, and domain and range. And we are going to see how these four concepts are studied, or are properties from the polynomials. Okay, so that's going to be our focus for today. We are going to focus on the graph and the x and the intercepts. Right. Later, maybe we are going to talk about a little bit of local, maximum, and minimum. But domain and range, we are going to save that for next classes, where the future class or next classes, where we are going to talk about asymptotes and restrictions. All right. All right. So another thing that I'm going to, so that's what we know so far, right? But what's the goal for test number 2? So the goal of test number 2 is that by the end of the study of the test number 2 material or polynomials, you are going to be able to go from the standard form of any polynomial to its factor form, and vice versa, right? So you will be able to factor any polynomial from its standard form, or to find the factor form of any polynomial, and vice versa. You can go from the factor form to the standard form, right? The factor form, it has multiple utilities, okay? And those utilities are, for our course, are going to be focused on how to identify some properties and characteristics of the polynomial. But for future classes, you are going to use the factor form to go further into more applications. All right. So let me show you an example of what you are going to be doing, or for an example for an example of what you are going to get from these units, right? So let's start with our subject here, which is this polynomial. All right, so right now this polynomial is in the standard form, or a simplified version of the standard form, because we are not using the addition operation here. We are using subtraction, but that means that 8 is negative, right? So let's say this is the standard form. Okay, so we have the standard form. So how are we going to go and write the factor form of this polynomial? What we need to do here. All right. So right now, I'm not going over all the details that we are going to study. I'm going to be very directly. I'm going to use a strategy to factor degree of 3 polynomials. And the strategy that we are going to use here, or the method that you are going to see, it is called factoring by group. Okay, you might have heard of that method on your previous math classes. Okay, so what I'm going to show you here is the goal of our test number 2 study. All right, what we are going to learn are the properties that allows us to do factorization by group. All right. So first thing that I'm going to do, I'm going to group my terms. I'm going to make 2 groups because I have 4 terms. So I'm going to first group the leading term with minus 8x. And you are going to see why I have selected those 2 for a group. All right. And the rest 2 terms are going to form a group as well. All right. So you are going to see me here not talking about any of these things, of the graph, the intercept, the factors. I'm not going to talk about all this, but I'm going to be using the properties that comes from these 4 concepts, okay, in order to use the methods of group factorization by group. Okay, I take into consideration all these properties, right? But in the surface, we are not seeing those. We are just seeing how we can group these 4 terms and how we can factor the polynomials. So we can write this polynomial from the standard form to the factor form, right? And this is what you want to take from test number 2. You want to be able to factor any polynomial. Okay, no matter what degree is, the coefficients, you need to be able to factor any polynomial. Okay. All right. So from the first group, I can factor out 8 because 8 is the common factor here, right? Also, I can factor 1x because on those 2 terms I have 3x here and I have 1x here. So now what it is left from that first factor, first group, is inside this parenthesis is x squared minus 1. Okay. For the second group, I can factor out just 7. All right. So now I have 2 terms. Okay, first, second. And from those 2 terms, there's a common factor. That common factor, it is not as a number, but as a quadratic factor. All right. So I'm going to factor out x minus 1. So I can do that here, this way. So x squared minus 1 Okay, so I factor out x minus 1 from both terms, and now what is left is 8x plus 7. Okay, Richard, why in the first one is it x? Okay, Richard, that's a great question. Why in the first one are you asking for this x squared? All right. That's a great question. So from the first term, we have x cubed, right? So this means, well, that we have 1, 2, and 3x being multiplied together, okay? From the second term, we have just 1x, right? So what it is common between 3x and 1x? Just 1x. So I took out 1x from this first term, so that means that now, instead of having 3, I have 2, hence my exponent goes from 3 to 2. So I take out this x. So now on the first term, I am living with just 2 copies of x. So x times x, I can simplify that as x to the power of 2, x squared, right? Does that answer your question? All right. Okay. Any other questions? All right. So at this point, this is now considered the factor form of the polynomial. Okay. So we have reached the factor form. We can go further, and we can do the following. I always prefer to have in my factors the leading term of each factor. See that here we have 2 factors, right? But inside those 2 factors, we have 2 more polynomials. We have an x squared minus 1 polynomial, and we have ax plus 7 polynomial. So what I like to have is my polynomials, all my polynomials on those factors. So the leading term, I want to have them in a way that all the leading terms are equal to 1. So I can do a trick here. Okay, so I can factor out 8 from these 2 terms. When I do that, I need to make sure that I writing the second term in a way that when I multiply back 8, I get 7, only 7 on the second term, right? So this is a trick here. It won't be necessary to do this on our class, right? But this is something that I want to do because I want to show you how the leading term looks like in the final factor form of any polynomial, right? This part here, this form, it is good. That's the factor form. That's completely correct. Okay, but we can go further and we can put our leading term as a factor here. Also, we are seeing 2 factors here. I can also order my factor based on their degree. So I would like to put the linear factor first, and then the quadratic factor last. Okay, and this is this is the form that I will prefer to work with or to reach out whenever I need to factor any polynomial, right? But the one that I see here, this one is good as well. Okay, you will see why I prefer to have my leading term here and not inside of one of the factors. Okay, so this is your goal. This is what you want to be able to do at the end of test number 2 study. You want to be able to go from any polynomial in a standard form, and you want to be able to factor it, right? So all the mathematical properties that are happening in the background of this method of factorization by group is the properties that we are going to be learning and we are going to study. Okay, we are going to see how these factors are constructed based on the polynomial that we have. Why we have 7/8 here, why we have -1 here, why we have one quadratic equation as a factor, and why we have another that's linear. Okay, all those questions are going to be answered in our study of this unit. So I don't know if you might be wonder what is the factor form. Okay, and to give you definition is when a mathematical expression is written using its factors and multiplication. Take this as an informal definition of what a factor form is. Okay, and let me give you 2 examples. A mathematical expression could be an equation or just a number. 21 is a mathematical expression, it's a number. How can we factor it? Well, we can factor 21 as 3 times 7. 3 and 7 are factors of 21, right? Because we use those 2 numbers to multiply them together and to get the value of 21. So 3 is a factor, 7 is a factor as well, and see that we are using multiplication. So we are writing 21 as 3 times 7. This is also known as, when we are working with numbers, 21 is a composite number, so prime factorization. Okay, so this is the prime factorization of 21. We use 2 primes number, 3 and 7, we multiply them together, they are factor of 21 to get 21, right? So that's the factor form of a number. In our subject here, we have its factor form. So you can see that the equation of this polynomial now is written with its factors. I'm using multiplication to put together those factors, right? Any questions so far? All right. So to reach our goal again, we are going to study the properties of the polynomials. Let me take our subject here. page 4, right? Yeah. Okay. So there you have it. That is our subject for our introduction. We have its standard form and its factor form. All right. This is also a function. This is a polynomial function. Can anyone guess what will be the shape of its graph? What will be the shape of this function? Can we guess? Or is there anything that we can use to know beforehand the shape of the graph? Okay. Think about the degree. Amanda, it is a cube function, not cube root function. Okay, cube root is this, right? But I like that you identified the exponent 3 as cube, right? So the parent function will be y equal x cubed, right? So that is the parent function. Let me put this here. So the shape of the graph of this polynomial, it will be this, something like this, right? Because its parent function is a cube function. Okay. What about the intercepts? If we have its graph, we can go and find the intercepts. We have here the x-intercept, the y-intercept, and we have 2 more x-intercept here. Though I do not know if this is the exact graph of this polynomial. The only thing that I know that its shape is going to be some like this. It's going to be a cube function shape because it's parent function. Okay. So we are trying to guess its function, its graph, based on its parent function. Now, if we don't have its graph, how are we going to find the intercepts? The x-intercepts, we know that in every intersection between the graph and the y-axis, we have an x-intercept. Hence, we know that for x-intercept, the y value of each of those points is going to be equal to 0. Okay, so the value of the function is going to be equal to 0. We have the function here. So basically, in any x-intercept, this equation is going to be equal to 0. Okay, that equation is going to be equal to 0. And here's the problem. We want to find those x-intercepts. Okay, the problem here is that we don't have a linear function. And we don't have a quadratic function. We don't have any techniques in order to find the x value or x values that makes this whole equation equal to 0. What is the value that we need to put in this equation? The input value in order to get all this equal to 0. It's going to be almost impossible to find those values without any knowledge of the properties of this polynomial. So we need to learn those properties before in order to solve this equation. In contrast, if we have this function or this equation 0 equal x plus 2, this is easy because there is no problem here with the leading term. So we just subtract both sides of the equation by 2 and we got that x is equal to. If we have a quadratic equation, well, we can use the quadratic formula. Right? So those are the techniques. So we have a linear function, we just apply any inverse operation to isolate for the variable x, and we got the answer. If we have a quadratic function, we could use the quadratic formula, and the quadratic formula is going to give us an answer. Now, here we have a problem. The degree of this polynomial is 3. So what are those techniques? What is the formula? What we need to do here? Okay. So here is where you want to use the factor form, all right? In real life, if we have a function that describe any particular situation, or if you are working with maybe fluids, I don't know. If you are working with a situation where after a long study you came up with an equation that represents the behavior or describe that situation, right? And then you are able to put that situation into a function. Knowing how to solve that equation when it's equal to 0 is going to be very important, because 0, when we find the 0 of that polynomial, that is going to be a pivot point to get more answers, right? I know that I'm talking about here mainly on how we can use polynomial in the future, how you are going to use polynomial in the future, right? But what I want to do is to put emphasis on how important is to be able to solve this equation. Okay, is to solve any polynomial that is equal to 0. That is going to be crucial on it is crucial on studies that are where those students use polynomial functions, right? So, what are the techniques that we have to solve this? We have its factor form, and why its factor form is so important here. Its factor form, it is important because we are now, instead of having 4 separated terms, now we have 3 factors, and those factors are together by multiplication. Hence, it means that if at least one of these factors is equal to 0, the entire equation is equal to 0, because we are multiplying here. If we multiply something by 0, it is going to get cancelled. So now that we have this factor form, we are able to find those values for x that makes this entire equation equal to 0. So we have 2 options. 8 is a constant number, so 8 here does not do anything here, so we can omit it, and now we can focus on the factors. From the first factor that we have, so if x plus 7/8 is equal to 0, then the entire equation is equal to 0. So we can solve this equation, and we know one of those values, one of those solutions. Okay, x equal to -8/7/8 is a solution to the equation of 8x cubed and so on equal to 0. All right, but we have another factor. This time is a quadratic factor. So if we solve this quadratic factor, we can get that answer. So on both sides, adding on both sides of the equation by 1, and then square root both sides. So x is equal plus minus square root 1 is just 1. Hence, we got the 3 solutions here. We have found the 3 x-intercepts of this polynomial, okay, by using the factor form, right? The y-intercept, on the other hand, is when x is equal to 0. So basically, we plug in 0 into x, and we got that value. Here, the standard form is the one that you want to use, because you can see that when we use the standard form and we plug in 0 into x, what is left, it is just the constant term. All these 3 terms are going to get cancelled, and this value here is going to be -7. So here is the y-intercept. Okay, so see how we identified the x and the y-intercept without getting into the graph of the polynomial, right? So, and you have seen the uses of the standard and the factor form of a polynomial. Any question? Okay. From this shape, we can see that this shape contains 2 turning points. So here we have the maximum, the relative maximum, and here we have the relative minimum. Okay, those are turning points, TP. Okay, TP, when I use TP, it means turning point. Turning point of what? Of the behavior of the graph. This graph, remember from test number 1 that when we learn how to identify the behavior of the graph, increasing from negative infinity to this point, we have an increased behavior, an increasing behavior. And then we have a turning point, and now its behavior changes into a decreasing behavior. We reach another turning point, and its behavior changes one more time as an increasing behavior. So turning points here are going to be important, because turning points are related to the degree of the polynomial. Okay. So I should take, okay, so the y-intercept ratio is -7. -7 when the constant term, see the constant term here, okay, the constant term always going to give you the y-intercept. When you have the standard form and you cancel all the terms using x equal to 0, the constant term is going to give you the y-intercept. So the y-intercept here is going to be -7, negative. Okay. Did I say positive 7 by mistake? Okay. If I said positive 7, the correct y-intercept value is -7. -7. Okay. Okay. So the relative maximum and minimum, they have multiple uses. Okay. For now we are going to use them, and we are going to identify them regardless of maximum or minimum as turning points. Okay, TP for short. Turning points are related to the degree of the polynomial. Okay, maybe I should need to copy and paste this, or just screenshot. Okay, so we are seeing two turning points, relative maximum, relative minimum. So we are going to say that here we have two turning points. What is important here is that this number is related to the degree of 3. Okay, these two numbers are not random numbers. They are related to one each other. The degree and the number of turning points, they relate in the following form. All right, so if we have a degree n, so I'm using n as a variable to represent the number of the degree, then I'm going to use an example. Degree of n at most, and that's the keyword, we have n minus 1 turning points. Let me give you that in a concrete example. The degree is 3. At most, we have 3 minus 1, which is equal to 2, turning points. At most means that we could have 1 or maybe even 0. I don't know if 0 is going to be possible, but I'm not 100% sure, but we could have just 1 turning point. If the degree is 3, at most we are going to have 2 turning points, but it could happen that we have only 1 turning point. In the other direction is, if we have m, I'm using m to represent the number of turning points, m turning points, at least degree is m plus 1. A concrete example, 2 turning points, at least degree is 2 plus 1 equal 3. So in the example, the degree is 3, the turning point are 2. Okay, but having 2 turning point means that at least we are going to have a degree of 3. But it could mean that we have it is possible to have 2 turning point and the degree being 4, 5, 6, and so on. Okay, this is important you to know, because later we are going to construct polynomials, and based on the turning point of the degree is when you are going to define, based on those is that you are going to define how many turning points and the degree. Okay. Okay, so from what we know so far, in today's class, we are going to talk about the graph of the polynomial function, the intercepts, or we are going to use the graph, the intercepts, and the local or relative maximum minimum for turning point and degree. Okay. Before entering to the exercises, which page is this one? Page 5, I believe. Okay. This is something what I'm going to discuss Now, this is something that you have on the worksheet of the day. And we are going to talk about polynomials, terms. And here I'm going to focus on the vocabulary. So when I'm doing the exercises, you will know to what I'm referring to. Again, our subject here is our little guy here. Oh, wait, this is incorrect. Our cube function here. All right. Okay. So we know we have the standard form and the factor form. From here, we know, excuse me, from the factor form, we can identify the leading coefficient, okay? From here, we have a factor. The degree of this factor is 1, so we have a linear factor. The second factor that we have here, or the third factor that we have here, because if we count 8 as the first factor, we have a quadratic factor here. All right. More importantly, the exponents here. Let me use a different color just to emphasize on that. So if we are not seeing an exponent, it means that the exponent is 1. Okay, so the exponent on the factor are going to be important. Okay, the exponent and the degree. Okay, if the exponent is 1, we are not going to write it. Okay, but I just want to emphasize that the exponent on the factors and the exponent on the leading term inside those factors. Okay, so the degree of the factors are going to be important. We are using them. So we have exponents and factors degree. Okay, we are going to be using though for talk about the multiplicity of the zeros of this polynomial. Okay, so there are all the parts that we are going to take into consideration, okay, from the polynomial. In the factor form is where we can see the multiplicity, is where we can see the linear and quadratic factors, and we can also take the leading coefficient. The leading coefficient is also present on the standard form. But from the factor form, we are going to use the factor form to identify all those pieces. All those pieces are important because from those pieces is where we are going to get the information of the property that relates to that polynomial. Okay, let's talk about multiplicity. So remember, we are going to relate the exponent and the factor's degree. What's multiplicity? So remember, we know we use the factor form to find the x-intercepts of this polynomial. The x-intercepts are related to, or is the same in the context of polynomial as the zeros or the roots of that polynomial. Okay, so the multiplicity goes related, it goes and define or affect the zeros of the polynomials. So we are going to say that this zero, this root of this polynomial, has a multiplicity of even or odd. Okay, and you will see why knowing the multiplicity of the zeros, knowing is that the multiplicity is 0 or odd, are important just in a moment. Okay, but the multiplicity is related to the zeros, to the x-intercept or the roots of the polynomials. Okay, and they are important because they are going to define the shape of the graph. So, but right now, from what we have here, I want you to see the relation between the exponent and the factor degree with the multiplicity. Or maybe more, we are going to see more the relation between the factor's degree, the exponent, and the degree of the polynomial. From the factor form, we have the first degree is 1. Okay, from the factor form, the first degree is 1. Okay, from x plus 7/8. And its exponent is 1. So we are going to multiply degree of 1 times that exponent. From the second factor, which is the quadratic factor, we have a degree of 2. And we are going to multiply that by the exponent of that factor, which is 1. Okay? So, from the first multiplication, degree of the linear factor, which is 1, times its exponent, which is, we have 1. From the second factor, we have degree of 2 times 1, that's 2. Adding together those two numbers, we got 3. And 3 is the degree of the polynomial. Okay? So this is important. The exponent and the factor degree, when we multiply them together and we get the sum of all those products, they need to be equal. It needs to be equal to the degree of the polynomial. Okay? So degree of the factor times its exponent. Okay? That's the product. That's the number that we are going to get from each factor. We are going to add all of them together, and the sum needs to be equal to the degree of the polynomial. All right? Equivalent concepts, and this is something that you have on the worksheet today. Okay, equivalent concepts, and we are going to be referring to the roots of the polynomial. Okay, so the root of the polynomial are going to be the same as. So on the left side, I'm going to write just the concept, the context. So if we're talking about polynomial, the roots of the polynomial are considered as the zeros of the polynomial. If we are talking about in the context of the graph, the root of the polynomial are going to be the x-intercepts. If we are talking about in the context of the function, we are going to get that the value of the function when when x is equal to the root of the polynomial is going to be equal to 0. the root of the polynomial in the context of linear factors we are going to use, let's suppose that x equal to r is the root, right? X equal to r is the root, so root is just a value for x. Hence, a linear factor of that polynomial is going to be x minus r. Okay, I know that here, this part here is confusing. Let me just give me a moment until I use concrete examples to show you how all this relates. And if we are talking about an equation, okay, so an equation of a polynomial, okay, this is just the general polynomial. So when we have a polynomial equal to 0, x equal to r is going to be a solution for that equation. Okay, let me bring this into the concrete concept using the example that we have, our subject. Oops. Okay. Let me arrange this in a better way, sorry. Okay, come on. Okay, that's better. Okay, I think that's better. So we are talking about the roots of this polynomial. So if we are in the context of polynomial, the zeros of this example are -7/8, x equal to 1, and x equal to -1. Okay, where does that number come from? We found those number here, the x-intercepts. Okay, hence we have the x-intercepts of the graph. So if I'm going to write the x-intercept as points, all right, so the points will be -7/8, 0. Let me use -1 here first, 0, and then +1. Well, to be consistent, I should put this one then also negative, and this one positive. Okay. Okay, so see that the roots of this polynomial, so if we are in the context of polynomial, the zeros are -7/8, -1, and 1. If we are in the context of the graph, its graph, so the x-intercepts are located at -7/8, 0, -1, 0, and +1, 0. For the function, we know if we plug in, well, I should use w because our example here is named with w. So -7 plugging into x, -7/8 plugging it into x of the equation, the value of the function is going to be 0, and that is going to be the same for -1 and for +1. All this is going to be equal to 0, right? From the zeros, see that here are the roots, -7/8, -1, and +1. So how can we construct the linear factors? Okay, and you are going to see now how this quadratic factor now becomes two linear factors. Okay, so directly from the roots or the zero of the polynomial, I'm going to take r here is the for the first one, it's -7/8. Here is going to be the first linear factor is going to be the opposite value of -7/8. That is why we have minus r. So minus -7/8 is positive. So it will be x plus 7/8, and this is a linear factor that we have here. See? Now, well, we are seeing a quadratic factor here. Well, this quadratic factor can be factored into two linear factors. In this case, so see that if we have x equal -1, so now one of those linear factors is going to be x plus 1, and the other factor is going to be x minus 1. Okay, so those are the three linear factors. So based on this, we have found the factorization into all linear factor of our polynomial here. All right, so see that this quadratic factor can be written or can be factored as a multiplication of two linear factors. Okay, and we are going to talk more about quadratic factors and its linear factor more in the later units. Okay, but just for today, I just want you to relate the zeros with the linear factors. Okay, I promise we are going to get back to x squared minus 1, why it is equal to x plus 1 and times x minus 1. Okay, but that we are going to talk about that when we start working with complex zeros. All right, and if we are talking in an equation sense, so if that is the equation, then the solution for this equation are going to be x equal -7/8, x equal -1, and x equal +1. Okay, so see that when we talk about the roots of the polynomial, we can talk about them in different contexts. In the context of polynomials, functions, on the graph, on just functions in general, linear factor, or as an equation. Okay, all those are going to be using this vocabulary. I'm going to be interchanging through the study of our test number 2 material or units within this context. Okay, but I just want you to know that whenever it's referring to zero of the polynomial, is the same as the x-intercept of the graph of that polynomial. Okay, this is something. With this, you can fill out the table that you have on the worksheet of the day. Okay, where it has the same things: graph, polynomial, function, linear factor, and equation. Okay. We're almost there. Okay. We have two more concepts to discuss, and then we can go and do our examples. Okay. But like I mentioned, test number 2 is the more heavy in terms of how much material you need to know and learn. All right. What can we do with the zeros of the polynomial? So we can build a polynomial from its zeros. And this is important because we have exercises where you need to build a polynomial from its zeros. Okay? And we have seen one of the examples in the previous unit, and then number 4, with one of the exercises where the zeros of the quadratic equation were given, and then we need to construct its equation based on the zeros, right? Okay. So how can we write the polynomial equation from its zero? We need to remember, let me use P, that the factor form of any polynomial function will look like this. Okay. All the factor form or the polynomials can be written in this structure. This is the factor form. And you can see here A is representing the leading term. Then we have the first linear factor with its exponent, then the second linear factor with its exponent, and so on. Okay? Again, this is a very mathematical definition, and it might confuse you because we are using multiple variables and subscripts and also three dots there. Don't worry about that. Just keep in mind, remember that we have a factor form, a structure. Coefficient, linear factor, exponent, linear factor, exponent, linear factor, exponent. Okay? That's what you need to have in mind, because if, for example, I give you the following. The zeros of the polynomial are -1, 0, and 4. And the degree of this polynomial is going to be 5. And now your task is to write down the equation of this polynomial. So how are you going to do this? So first, you're going to take the zeros. And you need to remember that the zeros are related to linear factors, to the linear factors of that polynomial. So if the zero is r, then the linear factor is going to be x minus r. Whatever the r value is, we just need to plug in it into this linear factor structure, x minus r. So we start with, we have -1. So from -1, we can construct x minus -1, so x plus 1. That's the first linear factor. From 0, we can construct, I think I can put this here. Maybe I shrink this. Now I can focus more. Okay, I think that's better. So 0, if we have a value of 0 for r, then we are going to use x minus 0. We simplify this and we get just x. When we have 4, positive 4, so having positive 4 as one rule of that polynomial, or a zero of that polynomial, well, we use x minus 4, and here we don't need to simplify anything, so those are the factors. So hence factors, linear factors. Okay, I'm going to start with x. X is the first linear factor that I'm going to use. I like to go in the following order. If I just have x, the variable, as a factor, that's going to be my first factor I'm going to write, right? Then I'm going to write down the positive. Usually I write the linear factor with positive constant terms and then the negative constant term, okay? So in the order that I prefer to write down my factor are x, x plus 1, and then x minus 4, okay? When a factor is just x, when the 0 is equal to 0, a value of 0, this usually in the past, a lot of my students have forgotten to include x as one of the factors, and this leads to mistakes on the exercises. Okay, so always remember that if you have r equal to 0, then you will have a factor of just of the variable x or whatever variable is being used there. Okay, so that's the first step, getting the linear factors. So what we have so far, remember this is the structure of the polynomial, right? That's the structure. So what we have so far is the leading term, we do not know it yet. What we have so far are just the factors what we do not know yet is the leading term and the exponent of those factors. Okay? So that leads us to the second step, that is going to identify the exponents. The exponent of those factors. And you need to remember that the degree of this polynomial need to be 5. So what are the exponents? So we know that the degree need to be 5. And we know that the degree of the factors times the exponent, when we add all them together, need to be equal to the degree. Okay? So from the first factor, we got a degree of 1. Okay? The same for the other two. So let me put here degree. Okay? If we are not seeing exponent, that's a degree of 1. Okay? This one is confusing because it is not clear where the exponent of x is and where the exponent of the factor is, right? So whenever you have this, the degree of the factor and the exponent of that factor is going to be basically the same, or is going to be a multiplication between those two. Okay, but it's not going to be explicit as for the last two factor, where inside the parentheses you can see the degree of the polynomial that is within the parentheses, and outside the parentheses where you can see the exponent. Okay, but this is not going to be a big threat for our class. Okay, just degree is just 1. Okay, the degrees for this one is 1 as well, and this one is 1 as well. Now, what we need to come up is with what are the exponent here. What combination of exponent can we use in order that when we multiply them together, and then we add them, okay, let me erase this, we need to have 5. The sum need to be equal to 5 because that's the degree. So in this situation, you have multiple choices. Okay, and remember that you are constructing an equation for a polynomial with zeros of -1, 0, and 4, and the degree need to be 5. That's all that you need to meet. Okay, the rest is up to you. So if you say that, well, I'm going to put the degree of this first factor equal to 2, and then my second factor is going to be, it's going to have a degree of 2, so and now I have 4, and then the other one is going to be just 1. Well, that makes up 5. That's one option. Another option could be, well, I want to use the first factor. I want to use 3 as the exponent of the first factor, and then 1 and 1. This is also 5, so that's good. Okay. Any combination, as long as you get 5 after multiplying the degree of the factor and its exponent, and then adding all them together, as long as you get a sum of 5, which is the same as the degree, you are okay. Okay. So, but here, to finish the exercise, we need to decide on which combination we want to use. So I'm going to use the first one. So I'm going to use 2, 2, and 1. 1, I just can omit it. Okay, so 2 times 1, 2 times 1 plus 1 equals 5. So I have a degree here of 5. The last thing that we need to come up is the leading coefficient. And again, the only that you need to do here is that you need to take care is that your polynomial meet these conditions, that the zeros are -1, 0, and 4, and the degree is 5. We have done that. Okay. So we have an infinite amount of choices for A. Okay. So, but you need to give one equation. You cannot give a set of equations. What I'm saying here is that at this point, this polynomial is meeting the initial conditions, right? So you are giving me all the possible polynomials with those conditions, okay? So A could be 1, 2, 3, 4, 0.5, whatever number, okay? This polynomial right now is meeting the zeros and the degree, right? So, but to give just one polynomial, you need to select a value for A. In this case, I'm going to select a value for A equal to 2. But the easiest one to select is 1, right? Do not select 0, because if you select 0, the leading coefficient as 0, then you cancel the entire polynomial. Okay? But you can use whatever value for A you want to use. So to complete my equation, 2x squared x plus 1 squared x minus 4, and that's my polynomial. Okay. Yeah, you have finished here. Why do I select A equal to 2? I have the option to select that number, and I want just is the first number that came up to my mind, so that's why A is equal to 2. You want to simplify things, A equal to 0. That's it. Any question? All right. We have one more concept to discuss, and it is the shape of the graph. Let's discuss the shape of the graph. And the shape of the graph is going to be determined by 3 properties of the polynomial. The leading, coefficients, sign. Okay, so the signs are positive or negative. Two, the degree of the polynomial. So we have here, we are going to have 2 options, even or odd, or 2 categories. And 3 is going to be the multiplicity of the zeros. So, and again, we have two categories here, even or odd. The first two determine the shape of the ends of the graph, and the third one determine the shape of the x-intercepts. Okay? And you will remember this from transformations, at least the first two. Let's start with the leading coefficient sign. Leading coefficient sign, we have two options, positive or negative. Okay, and let's mix out that with the degree of the polynomial. So for the degree, we have two options, an even degree or an odd degree. Even, you are going to relate even with parabola. And odd with cube. Okay, I am not saying that the polynomial is going to be a parabola or cube function. I just putting that there because the shape of the graph, we are going to have only two options for the shape of the ends. A parabola shape going up or down, or an cube shape. Okay, we remember parabola shape is this, right? Like an U. So for any even degree, we know that we are going to have a parabola shape in the ends of the graph. So what it is unknown, it is what's happening in the middle, okay? But the ends of the graph, so the end behavior of the polynomial function, if we have an even degree, is going to be a parabola. If the leading coefficient is positive, the parabola opens up, or the both ends go to positive infinity, go up. If we have a degree that is even, something like that, but the leading coefficient is negative, then the shape of the ends is a parabola going, like a parabola going down or opening down. Okay, so both ends go to negative infinity. For a cube shape, we know that we have something like this, right? Well, what we know for a polynomial, degree of 3, leading coefficient being positive, is that the left end of the graph goes down, right? Or go to the left and down, so to the negative position, let's say negative position, and the right side goes up and to the right side. Okay, that is when the leading coefficient is positive. When the leading coefficient is negative, well, we have a reflection. Let me see if I can put this here and reflect this. Right there. So when we have a leading coefficient that is negative and the degree is odd, so that is the shape of the ends. Okay. Yeah, left side goes up and left, and right side goes down and right. For multiplicity, so multiplicity of the zeros. So we have two options, or the multiplicity. I'm referring here to the exponents, okay? Exponent of the factor, not only the degree. Even, odd, even, we are going to read even with a behavioral touches, or touch, or cross. So here the x-axis. Here on x-intercepts, when the multiplicity of that x-intercept of that 0 is even, the graph touches the x-axis but stay on the same side of the x-axis. So it basically touches the x-axis and bounces it back. Okay, so there is no change in sign. So those are the two options. Okay, if the graph goes up, it reaches the x-axis, so that is the x-intercept, and then goes up again. So it bounces at the touch of on the x-axis. All right. If we go from the below, touches the x-axis and then goes down again. When the exponent of that 0 is odd, then the graph at the x-intercept crosses the x-axis. So there is a change on sign from positive to negative to negative from positive. All right. And that is the shape on the x-intercept based on the exponent of those factors, or the multiplicity of the zeros. All right. So we have reached the end of the introduction of polynomials. Now we are going to be working with the examples from Alex, but I'm going to take a 5-minute break, and after that we are going to go and do the examples. Before going to the examples, any question? All right, so we are going to get back here at 10 o'clock, and we are going to do example from Alex. All right.